All right, so this video is a continuation of the previous video for chapter 12. I'm sorry, chapter 13. Essentially, had an event that came up, and I had to put the Zoom meeting. I do all these things on Zoom. Put it on pause, and for some reason, when I resumed, I just had one more problem to go. But when I resumed, for some reason the speed on the playback was like faster than usual. For some reason, it makes it look like I'm doing everything in double time or something. So something happened. The rest of the whole video is perfectly okay, except for at the last moments when I paused it. So the last 17 and a half minutes of the previous video, I'm redoing that right now. So again, what I'm doing as a reminder is I'm basically redoing the last 17 minutes and 30 seconds of the chapter 13 video. And all that entails is me working out problem 14.62. All I did on that in that particular part of the video was work on OpenStack's 14.62. So that's all I'm going to do right here. Then I'll close this video off. All right. So again, this is a video that will be a supplement to the video. That is the official chapter 12 video. All right. So let's do it. OpenStack's 14.62. Okay, so that says the sun radiates like a perfect black body. With an emissivity of exactly 1. So that's what that's what a perfect black body means. Emissivity means perfect absorber and emitter. Emissivity of exactly 1. Okay, A says calculate the surface temperature of the sun. Given that it is a sphere. With a 7.00 times 10 to the 8th meter radius. And radiates 3.80 times 10 to the 26 watts. Into 3 Kelvin space. All right. B. B says, how much power does the sun radiate per square meter on its surface? All right, how much room do I have? All right, part C says how much power in watts per meter squared is that value at the distance of Earth? Okay, and then it gives you the distance of Earth as 1.5 times 10 to the 11th meter. All right. So problem reads: the sun radiates like a perfect black body with an emissivity of exactly 1. A, calculate the surface temperature of the sun given that it is a sphere with a 7.00 times 10 to the 8th meter radius and radiates 3.80 times 10 to the 26 watts in the 3 Kelvin space. B, how much power in watts per meter squared does the sun radiate on its surface? And then C, how much power in watts per meter squared is that value at the distance of Earth, 1.5 to 10 11th meters, right? So, all right, so I think that's all on there. So let's work the problems. All right, part A. So we want to, first of all, figure out what the temperature of the sun is. All right, and so what information do we know? Well, we know that the emissivity of the sun is 1.0. It is a perfect black body. So the emissivity is 1.0. One of the other things we want to know is, well, let's look at what the formula is. What formula are we trying to do? So we have the net heat transfer formula for radiation heat transfer. So Q net over T per time is, remember the formula, sigma EA times the quantity T2 to the 4th minus T1 to the 4th. T1 is temperature of the emitting object. Usually T2 is usually the temperature of the surroundings. Okay, so what do we know already? What is A? Well, A is the surface area through which power is radiating. In this particular case, it is a sphere. So you want the surface area of a sphere. So let's work that out. So first of all, we know that emissivity is 1 because it is a perfect black body. So that's given to us. And that's given to us. It tells us what the emissivity is. We know that that the surrounding space, outer space, is about 3 Kelvin. Very, very, very cold. Temperature of the sun is what we're looking for, T1. What area do we use? Well, again, the area of a sphere. That is the area through which power is radiating isotropically. Isotropically means in all directions equally. So we know that we have a sphere of radius r. The area will be given as 4 pi r squared. That's the formula for the area of a sphere. The surface area of a sphere. Actually, let me be more precise about this definition. We're literally looking at the surface area of a sphere of radius r. Let's compute that. So the area that goes into this calculation is 4 pi r squared, or 4 pi, the radius of the sun, we're told it is 7.00 times 10 to the 8th meters. And don't forget to square that, and you'll find that the surface area of the sun is 6.16 times 10 to the 18th meters squared. That is the power, that is the area through which the power radiates. The surface area. This is the surface area of the sun. The surface area. The area all around. If you were to wrap up the sphere, it would be the amount of wrapping paper you would take to wrap it up. I mean, that's the surface area. Okay, so I think we have everything we need to know. What we have to do here is, unfortunately, what we're looking for is this T1, and it's wrapped up in the parentheses, and I have it to the 4th power. So I'm eventually going to take the 1/4 root of everything, right? So what I got to do is I'm going to start off by flipping around the equal sign. So again, make note of these values. We're going to use them later. All right. I have my real estate challenge. So here we go. So I'm going to put the left side on the right and the right side on the left. So I have sigma EA times T2 to the 4th minus T1 to the 4th. And that's equal to Q net over T. By the way, we're given Q net over T. I didn't specify that as well. Q net, let's kind of talk about that for a moment. Q net over T is actually given to us. That's the power radiated. Again, it's heat per time. That's power. Energy per time is power. So we're told that that's 3.80 times 10 to the 26 watts. Now, remember, heat has a sign convention to it. If a system is losing heat, it's negative. If it's gaining heat, it's positive. So we really want to write here that this is negative 3.80 to the 10 to 6 watts because the sun is radiating heat away from it. All right. So again, that's really important to note here in the various values of no. We know the whole content of Q net over T. We know that that I have it in a fractional form, but it's really the power. All right. So we solve for this. First thing we want to do is divide both sides by sigma EA. So I would have T2 to the 4th minus T1 to the 4th is 1 over sigma EA times the quantity Q net over T. All right. Now what I'm going to do is I'll put the T1 to the 4th on one side and the sigma EA on the other side, and I can write that T1 to the 4th is equal to T2 to the 4th minus 1 over sigma EA times a quantity Q net over T. Then all that's left to do at this point is take the 4th root. Remember, I have this equation. The right-hand side the left-hand side is T1 to the 4th. I want to get T1, so I take the 4th root of each side. 4th root of the left side, it gives me this T1, and the 4th root of the entire right side. So what I now get is T1 is, I'll put brackets, big brackets. So it's going to be T2 to the 4th minus 1 over sigma EA times Q net over T and brackets, and all of this is to the 1/4 power. Take the 1/4 power of each side. So you calculate all of this, get a value, and then take the 1.25 power, caret in your calculator and 0.25 power of all this. All right, so let's plug in the numbers now. We're ready to go. So I'm going to erase all this. I'm going to continue. I mean, again, if I had more whiteboard, I would just continue and leave everything that you see written, but we don't. So T1 is equal to, okay, T2 to the 4th, that'll be, sorry about that, oops. All right, having a little issue with my whiteboard here being centered. Let's see. All right. Anyway, T1 is going to be T2. So I have 3 Kelvin to the 4th minus, okay, so oops, I need as much room as possible. They're fairly large values. So again, T1 equals brackets. I have 3 Kelvin to the 4th. That's the temperature of outer space. And then I have 1 divided by sigma, 7 Boltzmann constant, 5.67 times 10 to the negative 8. And that's watt, or I guess it's my opus refers to as joules per second meters squared Kelvin to the 4th. I got that. I need my E. Well, that's simply just 1.0. The A, I calculated that earlier, is the surface area of the sun, 6.16 times 10 to the 18th meters squared. Great, I got all that. And then I need to multiply all that by Q net over T. And that's going to be the, and I'll just put that up on top here. That'll simply be negative 3.80 times 10 to the 26th watts. And that's all to 1/4 power. So you want to be careful here in that you have an algebraic minus sign, in the formula, but then there's another minus sign from the very fact that the heat is a heat loss. So there's 2 minus signs at play. A minus is going to give you an addition. So it's going to be this plus this. It's going to be negative of a negative. All right. When you work all this stuff out, you calculate all of this. You take the 0.25 power of everything. You'll find out that T1 is we get 5,740 Kelvin, which is about the known temperature of the sun. So it's very hot. 5,740 Kelvin. That would be the answer to part A. Okay. Now we want to keep note. Or actually, we're good with this. We don't. I mean, this is part A. We don't. Part B and C do not depend on this. So I'm going to erase all of this. We have the temperature of the sun. Now, the next question is part B asks, how much power does the sun radiate per square meter on its surface? Power per square meter, power per area, we call that the intensity. So the intensity is the power divided by the area. And we know the power is Q net over T, which again is 3. And I'm not going to, in this particular case, I'm not going to worry about the signs on the sheet because I'm just calculating the overall intensity. So Q net, we're told, is 3.80 times 10 to the 26 watts, right? That's the power, Q net over T. And so now what area do we want? Well, we want the surface of the sun. We want the area. So it's basically the power that's radiating isotropically through what area? Well, the surface of the sun. That's that surface area that is going to be computed. So at the surface of the sun, that is, you always want to be calculating, and intensity is always the power over an area. What area? Well, you pick that. So in this particular case, it's the surface of the sun. We're going to realize in part C, it's going to be a sphere whose radius is equal to the Earth's sun distance. Okay, so we'll get to that. But again, what area are you talking about? Well, now it's the area of the surface area of the sun, which we've actually already calculated. We already computed that. So we're ready to go. This is a very short part B. And that is, it's going to be this power, 3.80 times 10 to the 26 watts, divided by 6.16 times 10 to the 18 meters squared. We'll find out that the intensity of at the surface of the sun is huge. It is 6.17 times 10 to the 7th watts per meter squared, 61.7 million or megawatts per meter squared. Okay, very no life form is possibly going to exist in such close proximity to the sun. That intensity is out of this world. So you're not going to be able to do that. So again, this is a very, very intense area because you're talking about a sphere that's relatively small in retrospect. It's much bigger than the Earth, but but again, you're talking about the surface area of what? You're talking about the power radiated per what area? The surface area of the sun. All right, so that's why we use this formula. All right, part C, very similar problem. I'll just change this to a C, and a lot of this I'm just going to kind of keep written the way it is. So again, we're still talking about the sun radiating the same power. But now we are looking at what is the intensity at the distance of the Earth to the sun. Again, the same power is still radiating outward everywhere. But what you're going to talk about now, instead of the small sphere, which is the sun, surface of the sun, we're going to consider the Earth way out here. And we want to figure out, the sun is going to radiate all isotropically. Now here, you want the intensity, well, it's a much smaller sphere, so it's the radius of the sun. But now we want to figure out how much intensity is at any object, not just the Earth, but any object that's a distance equivalent to the Earth-Sun distance. So what do? Well, we draw a sphere that's about the size of the radius of the Earth. So we're going to draw a big sphere. Again, big sphere. This is a sphere. And this sphere is going to have a radius equal to the Earth-Sun distance. We'll call this R1. So R1 is going to be 1.50 times 10 to the 11th meters. We want to capture all the same power, but distributed over a much, much, much larger sphere. A sphere has a radius of the Earth-Sun distance. And figure out how much radiant intensity is through that kind of a sphere. We realize for the sphere equal to the with a radius equal to the radius of the sun, the intensity is intense, right? Incredible. And that's because you have a much smaller surface area. Now we're going to really expand out the surface area, make this area the denominator much larger, and figure out what is the power per unit area over this bigger sphere, this sphere that's equivalent, that has a radius of the Earth-Sun distance. All right, so that's what we're doing here. We'll calculate what we normally call the solar constant. So we got to calculate that surface area. Well, that surface area, we'll call it A1. A1 is going to be 4 pi R1 squared. A1 is 4 pi. Okay, what do we use now? Well, the Earth-Sun distance, 1.50 times 10 to the 11th meters. Don't forget to square it. You'll find out now that area, and when you do that, you calculate that area, it's going to be 2.83 times 10 to the 23rd meters squared. Okay, now, what's the intensity? This is the intensity at the Earth, a little E for Earth, if you will. Okay, what's that going to be? Well, it's going to be the same power. The sun still radiates the same amount of power, 3.80 times 10 to the 26th watts, divided by 2.83 times 10 to the 23rd meters squared. Okay, and you'll find out the intensity at the distance of the Earth is going to be 1,340 watts per meter squared. Okay, we usually call that the solar constant. Normally, the number I remember is about 1,400. Usually, the number that most people quote. You ask them, some physicist walking in the street, "Hey, what's the solar constant?" Usually, he or she will say 1,400 watts per meter squared. So what we have here is maybe a little more accurate number, 1,340. But again, there's other factors that come into play. There's emissivity and things like that too. So anyway, Because that is, the direct calculation. That is, again, irrespective of anything of what the Earth is made out of or anything else. You put any kind of object, a mirror or anything, at the distance from the center of the sun to the center of the Earth, you're going to get this value. This value is a pure geometry calculation. All right. And with that, that is the end of the supplement to chapter 12.